Now that you have been exposed to the concept of hybridization, we can now talk about single, double, and triple bonds. Double and triple bonds are called multiple bonds, and that's the topic of this section. What we begin with is, what is a single bond? Again, these sections are really important. They apply to so many other things you're going to learn as you move along in your college career. A single bond is also called a sigma bond. Its picture is above. Notice the electron density is concentrated on the axis. Now, I always ask this question on a final exam when I wrote it, and only 10% of the people would get this right. When we call an internuclear axis, imagine it being an x-axis. Notice how where we have the overlap, that's what we mean about electron density concentrated on the axis connecting the nuclei. It's factual. For a hydrogen molecule, it is two hydrogen atoms, and we have the s orbital overlap. For chlorine, we have a p orbital overlap. And as we taught in the last section, for BeF2, we have an atomic orbital s and an atomic orbital p, and that atomic orbital s and the atomic orbital p, they give us sp orbitals, and there are two of them. They are the hybrids. So a word question can involve any of the facts that are on this slide. On the next slide, we talk about a double bond. Let's talk about the differences. A double bond is also referred to as a pi bond. Look at the difference in the picture. For the sigma bond, we had density on the internuclear axis. Let's just call it X. But notice for the pi bond, the density is not on that axis. This double bond results from what we call side-to-side overlap of the p orbitals. Imagine that they once looked like this. What they are doing is they are overlapping in order to form this pi bond. These p orbitals, we say they are not hybridized. They are perpendicular to the internuclear axis. By that I mean there is our perpendicular. And we have electron density above and below the nuclear plane. Let's just call this an XY plane. All right, so that's what a pi bond is. The most important thing is there's no probability of finding an electron and that internuclear axis. Notice this is empty, okay? So essentially there is no electron along that axis, and because of that, we know there is less overlap, and from that we can say a pi bond is weaker than a sigma bond. So how is this represented? Well, the molecule we're talking about as our poster child is ethylene. That is the precursor to polyethylene. If I have a ball and stick type model, it could look like this. If I draw it out, it looks like that. So what do all those colors represent? Well, the blue, those are the hydrogen s orbitals. The purple, those are the sp2 orbitals. Those are the hybrid orbitals. And what we have left are the pink, and the pink represent the pi orbital. So again, when you go to organic, the professors will say, didn't they teach you this in Gen Chem? Yes, we did. So please keep in mind the sigma, keep in mind the double bond, the pi. Let's see what's on the next slide. What we have on the next slide is the triple bond. Notice I've said it is one sigma bond and two pi bonds, a favorite midterm question. Just like on the slide before, we have a pi bond above and below. This would be my above and below. But now that we have a triple bond, we have one that is in front and behind. So here would be my front, and here would be my behind. Again, take some time to look at it. If I let these orbitals come together, like let's just say this one, what it's going to look like is this overlap. So you have electron density above and below the internuclear axis. You have electron density in front of and behind the internuclear axis. So let's apply this. If I have the molecule methane, I have 4 sigma bonds. I'll just draw it like I would with a Lewis structure. Each of these is a sigma bond. We know the carbon, I guess I have to draw it, is a tetrahedral. And it has, that is its both electron and molecular geometry. We also were taught in the last section that each of these bonds is an sp3 hybrid bond, okay? Next we have ethylene, where we now have a double bond. So one of the questions they'll ask you on the exam is how many sigma and how many pi bonds does a molecule have? Well, I'm going to start with that. I'm going to say there are 5 sigma bonds and 1 pi bond in this ethylene molecule. So there it shows 1 sigma bond and 1 pi bond. That is where they are referring to the double bond. But overall, that's what the molecule has. Since there are 3 electron domains, we know that it is trigonal planar, and since we don't have any lone pairs, that is both its electron and molecular geometry. We also know from the last section that each of these carbons is sp2 hybridized. And as I talk, I realize all of this is jargon. If I were to attend a talk in another area, I may not follow anything they're saying. That's why it's so important for you to take Gen Chem section by section by section, because as you can see now, our language has gotten much more specific than it was day one. So what's left in this section? Well, what we have is acetylene, all right? And I have some statements to make about that. If I talk about the triple bond, we have 1 sigma and 2 pi. So if you can imagine that's a triple bond, there is the sigma, there is a pi, and there is a pi. Both carbon atoms are linear. There are just 2 electron domains, and that would be their both electron and molecular geometry. Both carbon atoms are sp hybridized. The sp orbitals, they are from the carbon-carbon and the carbon-hydrogen bonds, those original atomic orbitals. There are also 2 unhybridized p orbitals on each carbon atom, and they are the ones that are going to form the 2 pi bonds. 1 pi bond is above and below the plane. The other pi bond is in front of and behind. I sort of repeated exactly what I said before. Students have struggled with this, so please take some time and ask some questions. So, we need to also mention now, not only is there pi bonding, there is delocalized pi bonding. Think back to what a resonance structure is. That's where we could not draw a single Lewis structure. We had an ion like the nitrate ion, and what I want to introduce you to here is benzene. So let's do the nitrate first. I put down the resonance structures that we had in chapter 8. I put down, let's just say we're going to have a localized pi bond in here where we have the overlap of these unhybridized p orbitals. Well, what's to say that's the only way to draw it? If I can draw a resonance structure, I will then have delocalized pi bonds. Again, something new for you to learn. When you take organic, this is all the different ways that benzene can be represented. Instead of putting carbons down all the time, because we have many rings in organic chemistry, organic chemists tend to take a shortcut, and they will draw those hexagons. They will designate the resonance structures. Here's where we have our, double-headed arrow. And you can see that the bonds are drawn in different spots. Another common way to draw benzene is with a circle in the center, or I should call it an aromatic ring. So what we have in this section is a picture here of the sp2 hybridized orbitals, where we have the p orbitals of carbon overlapping with the atomic orbital of hydrogen. And then what we have here are those p orbitals. Notice they are just standing up straight like little soldiers. If I look at that picture and I move myself over here to the left, you can see there's two different ways to draw what is called a localized pi bond. Since we have some resonance, we can also draw a delocalized pi bond. Now, they'll spend a lot more time on this in organic, but try to grasp it in our class. Ask some questions. It'll put you ahead next semester. Where can I have an example? Well, if I take a scanning electron microscope of the eye and I enhance it with color, you know that your eye has both rods and cones. A little bit further. What's there? Well, this molecule here, when light enters the eye, it is absorbed by a molecule called rhodopsin. When it absorbs, it is going to break that pi bond, and what will happen is there is rotation. So here's the pi bond. There will be a 90-degree rotation around that double bond where the retinol separates from the part called the opsin. But for you neuro people, the most important thing is it triggers a nerve impulse to your brain that your brain interprets as vision. It only takes 5 molecules to undergo this process, resulting from 5 photons of light. I think that's pretty interesting. We haven't had a lot of really interesting applications in this course, but everybody's looking out with their eyes to see things. That's why when you have an intense white light, you get what they call temporary blindness because you've overwhelmed the system. I like this. It's an application, okay? So, what did we tell you so far? Well, we talked about something called valence bond theory, and that was a great model that had to do with molecular geometry. Oh, you had the pleasure of learning all those different geometries. Now that we have hybridization, it allowed for bonding. If electrons were originally there, they were not available to be shared, so we had to hybridize them. But there's still a small issue that remains, and 2 properties that cannot be explained are magnetic and spectral properties. And for this, we need what is called a third theory called molecular orbital theory. I'm finding it a lot easier than I did in the past. I'm hoping that my explanation in the next section will make it clear to you. But realize these are 3 distinct things. Valence bond is one, hybridization is the third, and MO is the most sophisticated.